Let's wait for it to be recorded. Okay, now it's recorded. Okay. Right. Did you guys remember this question? It was from topic 2. This is question 5 that group 8 presented. Just a reminder, in case you have got any question, I will not be able to see the chat box here. Could one of you unmute your microphone and just voice out your question, or maybe remind me that there is a question on the chat box. Okay, so otherwise I'll just go on with that. Right, so just a reminder, we have got this question where we have got sucrose, degraded into a product or converted into products with the enzyme called sucrase. And enzyme concentration initially was at 1 millimole per liter. Sorry, this is the sucrose concentration initially was 1 millimole per liter. And then the enzyme concentration CEI is 0.01 millimole per liter. And you were given this following experimental data. The time was taken in hours because whenever you're dealing with a biochemical reaction, normally it's a very, very slow process. Most of the chemical reactions, they are in minutes or even in seconds if you have got very fast reaction. But for biochemical reaction, normally they are quite slow. And then you will see that the time is normally captured in hours. You have basically got the concentration profile here. You're starting with 1, and then this is matching with the one given in the problem statement here. So this is 1 millimole per liter. 1 millimole per liter. This is capital letter L. So if you plot the concentration profile, then you see that you're going to get a nice curve. Okay. Now you want to do curve fitting, and you have seen the solution from group 8 that you can manipulate this nonlinear equation. Why is this equation nonlinear? Well, because you have got the variable CA on the numerator as well as in the denominator. Okay. The rest of them, they are just either parameters or constant. For example, here you got K as a rate constant, and you've got the initial enzyme concentration, CEI, and then there is Michaelis-Menten kind of parameter M here. Okay, this is quite nonlinear. So how do you solve this nonlinear equation? Group 8 suggested that we linearize this nonlinear equation. What does it mean? That means that we convert this nonlinear equation into a linear equation. Okay, so this is their work solution here. We know that the rate minus RA is nothing but minus dCA dt, and this is equals to the term that you see on the right-hand side of the equation, which is this part here. So minus RA here is nothing but minus dCA dt. And what you can do is that you see that we have dCA here on the numerator, and then we have got CA on the numerator and denominator on the other side of the equation. So bring the whole thing here as if you have, let's see, one variable of CA over CA plus M to the left-hand side of the equation. So when you bring this to the left-hand side of the equation, then you're going to invert from CA over CA plus M to CA plus M over CA. And then you integrate from CA naught to CA. So the minus sign here remains. On the right-hand side of the equation, you are left with K and CEI. So you bring this dt to the right-hand side of the equation, and then you integrate everything with respect to time. And noting that K and CEI, they are just constant values. So you can bring them out of this integration. And after you integrate, so basically I made a note before that this term here, because you have got only a single denominator, then you can break it into two terms. One is CA over CA, which is this part here. This is CA over CA. And the other one is M over CA, which is the second part here. So you can integrate the first term with respect to the concentration, CA, and the second term. And then noting that CA over CA is just 1. So that's why once you integrate and then put in the limits from CA naught to CA, please do not forget to put in the limits. You're going to get CA minus CA naught from the first term here, and then M times Basically, this is ln of CA minus ln of CA naught. And you know from what you have learned in math, in calculus or algebra, that once you have got ln of CA minus ln of CA naught, then you can combine it to become ln of CA over CA naught. So you simplify the equation. On the right side of the equation, this is quite simple because you are integrating basically 1 dt, and this is just t, because you are integrating from 0 to t. And what you can do right now is try to find the common term so that when you plot, you are plotting something quite simple to be solved. And then group 8 decided that they wanted to plot T over CA naught minus CA versus, if you look at here, it's ln CA naught over CA over CA naught minus CA. Okay, so this is coming from their simplified equation. Okay, right. So you notice that they have plotted a linear correlation between this variable and that variable. Yeah, and they have got a trend line. And I'm sure that you know how to generate the trend line in Excel already. Yeah, please let me know if you do not know how to do it. But I'll show you how to do it later on. So once you have got the linear equation with the R square value, and R square value is quite good because this is quite close to 1, right? And you know from your prior knowledge that you have got the slope of the line, which is 0.9879, and then the intercept of 5.0497. So what are these? So if you are plotting this equation here, right? Basically, you have got 1 over KCI as your, what do you call it, y-intercept. And from there, you could solve for K, right? So you plug in the y-intercept, which is C, if you have the form of y equals to mx plus c. And then you can solve for K. And K is around 20 per hour. Okay? That's the unit for K. And then once you know the K value from the y-intercept, because Ci here is just a constant, then you can go to the slope and then you can solve for m. Yeah, because K is known, Ci is also known, so m is unknown. So from the slope, you can solve for m, and m was found to be around 0.2. Okay, this is one solution. The other solution is you could note that there is a CA in the numerator and CA in the denominator. So why not we bring this CA from the numerator to the denominator and simplify the equation to become like this. So this is basically CA over CA. It becomes 1. And then this is nothing but M over CA. Okay. And then bring this to the right hand side of the equation. And then dt to the, this to the left hand side of the equation. And the other one, dt to the right hand side of the equation. So you integrate also from CA naught to CA. And don't forget the minus sign. And the other part is easy because it's just integration of KCI with respect to dt from 0 to t. Okay. You are going to get a very similar conclusion from here, but you have a different equation to be plotted. So the left-hand side of the equation here is your y-axis. So it is basically ln of CA naught over CA divided by CA naught minus CA. And then you plot it against T over CA naught minus CA. So if you notice that T over CA naught minus CA is group 8's y-axis, and then the x-axis is here. Okay. Normally, I would suggest that we try to be consistent in such a way that the x-axis refers to the variable that you manipulate, and then the y-axis refers to the variable that you observe. Yeah. Okay, so that's why it is better to have this one as your y-axis, and then the variable corresponding to the time in your x-axis. Yeah, so once you plot, you're going to get the same result basically. And further to that question there, okay, somebody suggested to me that, well, you have learned about some built-in function. So can we solve the equation, can we solve the problem that we saw before in question 5, yeah, through a different method? Yeah, I just wanted to remind you that we basically did what we call linearization of a non-linear equation before. Yeah. So the previous two solutions was what they call it, linearizing a non-linear equation. And you remember that you learned about goal-seek, not goal-seek, it's a goal-seek. Sorry, my apologies. It's a goal-seek. Right. So basically, you have learned about the goal-seek function in Excel last year. Okay? You remember that you have the Excel or the spreadsheet session in PIC or B48BA. You also learn VBA, which is Visual Basic for Application, where you need to run macros and probably you need to write a program. Okay, so you basically have been exposed to the goal-seek function, but the question is that can we use the goal-seek function to solve the problem? Anyone who wants to take a guess, can you or can you not use a goal-seek function to solve the problem? Maybe you can just type in your answer here. Anyone? Anyone who wants to take a guess? Is it a yes or no? What is the answer? Is it yes or no? No one? Yes. Okay. So thank you, Zihao and also Pei. Your answer, both of you say yes. Well, probably because you've been exposed to what I call it, a problem where you solve only one variable, right? So once you solve one variable, definitely you can use goal-seek. But if you look at the problem here, okay, so let me go back and try to see the problem. Okay, you have got two variables. One says k, or two parameters that you want to solve. One is k, the other one is m. Okay, so goal-seek has a limitation. If you want to solve this problem using goal-seek, you could only do so provided that you only solve for either k or m, not both. Okay, so the answer for it is that no, you cannot use the goal-seek for this purpose because you are solving k and m simultaneously. Yeah, so basically you want to use the Excel solver to solve this nonlinear problem. Can I check with you whether you have used Excel solver before? Would you like to know? Okay, Zihao say no. What about the rest of you? Have you been exposed to Excel solver yet? Or not the solver? Okay, good. Thanks for the feedback. I'm sure that you would appreciate. Yeah, tak ada gaming. Okay, so I'm sure that you will appreciate if we go over something beyond what you have learned before, because I thought that Excel solver is quite important for you to become a very successful engineer later on. Yeah, this is a minimum skill basically that you need to possess before you can call yourself as engineer. Okay, so how do you solve it? Okay, let's go to the Excel and let's go to this topic. Okay, can you open Excel from your laptop or from your PC and key in all these values here. Basically, these values are the values coming from the problem statement. Okay, so basically, can you key in all these values here from 0 to 11 for the time in hours, and then concentration from 1 all the way to 0.0025 in vertical format, meaning that it is formatted in column rather than in rows like this. Okay, so the example is here. I just wanted you guys to understand how to do it. Okay, please do so and key in. And once you do that, can you let me know that you have done so and ready for the next one? Let us spend about maybe 1 minute for doing so. at the most maybe 2 minutes. Okay, right. So just key in like this, and then after that you just type in CEI equals to, this is the data, yeah, 0.01 millimole per milliliter. And don't worry about the slope and y-intercept here, because this one came from the previous solution. The previous solution came from this equation here, from the trend line. Okay, so I think if I'm not mistaken, I discussed the solution with you before. Yeah, so this is basically plotting that ln of the concentration ratios versus the time divided by Ca naught minus Ca, and then you have got y equals to mx plus c, and from there you can solve for the slope and also y-intercept. This is the y-intercept and this is the slope. Okay, right. Okay, I'll give you about 1 to 2 minutes to do so. Okay, so can I check whether you have done entering all the experimental data in Excel? Done. Okay, good. Right. So the next step would be, well, you have got time versus concentration, and if you were to plot this, you can just highlight from T, yeah, until all the way to 0.0025 here, because here is what do you call it, up to 3 decimal places, and then you can check on the scatter plot, and you can see that you have got a nice profile. Okay, this is a concentration profile. The y-axis is the concentration and the x-axis is the time from 0 to 11. Okay, can you see that you have got a nice linear equation here, and then maybe a slope, a curve here, and then this one is sort of leveling off. Okay, so from there, you would go back to the Michaelis-Menten equation and then try to see whether you understand the equation or not. Okay, so what is minus RA? Minus RA is nothing but, okay, your friend has done it here. Minus RA is nothing minus dCA dt. And this is equals to the term on the right side of the equation. Okay, so how are you going to solve it in Excel? Okay, what you could do is that you create a column called minus dCA dt, and then from there you could also have another column called here is the MM model, which is the predicted values. So MM refers to the Michaelis-Menten model that we have. So what is minus dCA dt? So in order for you to get a rough value for it, we can convert this into delta CA over delta T. Yeah? Don't forget the minus sign there. So what we have here is that we cannot start with the first row because if you look at the values for the delta, it is basically CA2 minus CA1 divided by T1 minus T0. Okay, if you start with the first row, then there is no value above that. Okay, and you're going to get an error. So we are going to estimate d minus dCA dt in such a way that we have got minus delta CA over delta T. Yeah, so delta means you take the difference between the two subsequent values. So CA2 minus CA1, T2 minus T1, or vice versa. So if you've got, let's say this is CA1, then this is CA0. Okay, right. And then you copy down the formula. Click on here, you can see a T sign there, and then drop all the way down, and that is basically copying all the formula. And then you check the last value, whether your formula is correct. And this is B22, which is 0.003 here, minus 0.006, okay? And then you have got 11 minus 10, which is 1. So basically, you have got minus delta CA over delta T in the first column here. The model here refers to the one on the right-hand side of the equation. Okay? So you can see the formula here is that you have got K times CA times CEI divided by CA plus M. What is this formula all about? So let's go back to this equation here. Let me go back to this one. Okay, this one is clearer. So minus RA is nothing but minus DCA DT. Okay, let me write that down here. So minus RA is nothing but minus DCA, oops, DCA DT. There is something happening since last week. I don't remember. I don't know what happened here, but this is minus DCA DT. And then the term on the right side of the equation is your so-called predicted value that we are going to put in the MM model column. Yeah, basically, you want to estimate this part here. So this is what you do. Yeah, key in the formula, and the formula is using the K value here. So you want to set up M equals to a value, and then K equals to another value. Okay. And then use this value here in the equation itself, and don't forget to put in the dollar sign before the column number, column and before the row number, and multiply by CA. CA here, you don't need to put in the dollar sign because once you copy down, you want the value to be changed. Okay, but here once you have the dollar sign before F and dollar sign before 29, that means you want to fix a number, which is in this case here the cell representing the K value. And similarly, there is a cell representing the CI value, which is B24. And then lastly, you want to fix also the M value, which is F28, which is this one. Okay. So can I check with you whether you understand what to enter in here in this cell? This cell is F12. Can I check with you whether you understand what we discussed just now? Is there any question? All right, so good. Let me proceed. Right, so the same thing as what you did before, you copy down the formula because you have ensured that all the cells that you want to remain as they are without changing their values when you copy down. You can just copy down like that. Okay, and then ensure that the last one, when you copy down, the last value will take up the appropriate cell for the CA, but then you want to ensure that CI remain CI, M remains M, and then K remain as M. K remain as K. Right. Now you have ensured that. The next thing that you want to do is to create another column, call it SE or squared error. What is this squared error? So squared error means, yeah, if you look at the formula here, is the difference between these two values, okay, and then you square them. Okay, let me repeat that. So you take either this one, 0.16 minus this one, 0.16, and after you got the answer, you square the answer. That's why you can see there is a parenthesis here. So it doesn't matter whether you have this value here in blue cell minus the one in the red cell or vice versa. Because once you square them, the sum, the squared error will be a positive value. Okay. So just to be clearer, initially I do not know what is my M value, so I can just estimate that my M is just a positive number, maybe 1. And then K, I also don't know, and just put in 1 here. Although from my linear, what I call it, linearization of the nonlinear method, I could find m and k from the slope and also from the y-intercept. But let's say I don't want to go to the lengthy process of linearizing a nonlinear equation. I'm just going to start using solver. Yeah, so you can just ignore the solution on this red what I call it block here. So if I start with m equals to 1 and k equals to 1, you can see that my model here that is predicting what is supposed to be on the right-hand side of the equation give me 0 values. Whereas it's supposed to give me 0.16, 0.16, 0.15, 0.15, and so on until 0. So 0 is supposed to be the last value here. But the prediction is showing that you have got 0 all over the place here. And then when you look at the error, yeah, the squared error, you have got some error here. And then when you sum all this error, the value at the bottom here is what we call as SSE. So let me write that down. SSE equals to. So SSE refers to the sum of squared error. Okay. So in this case, SSE equals to 0.1229. So let me ask you, what do you expect a good value for SSE to be? Can you write down your answer here? What would be, yeah, it will be 0. Yes, you have got the answer right. It's supposed to be 0, right? Because you want the error to be a number, if not 0, a number very close to 0. Okay. So how do we ensure that this number here can be close to 0, as close to 0 as possible? So one thing that we could do is try to type in, let's say m. I don't like 1 because that give me what I call it, SSE equals to 0.12. What if my m goes to, let's say 10? And it doesn't change too much. It's still 0.12, 0.13, right? So let me revert m to 1. And then what if my k is 10? Then I can see that SSE has reduced a bit from 0.12 to 0.08. So if m is increased double up, now my SSE has been reduced to 0.04. But that is probably not the most efficient way of doing so, because this is just like a trial and error, correct? So what if I told you that you have a built-in function in Excel, we call it solver, that you can use in order for you to find m and k values very, very efficiently. Yeah. So how to do it? Right now, can I check with you whether you have successfully entered all the equations here? Do you need maybe 1 or 2 minutes to just enter all these values and then enter the SSE and then sum up all the the squared error so that you got SSE? Yeah. If not, then can you spend about 1 to 2 minutes to do so? So SE refers to the squared error. Okay? So SE equals to squared error. Okay. So SSE equals to the sum of squared error. Okay. So you can see that from here, this is the squared error. Why we call it squared error? Because we take the difference between the two. Yeah, one is the one coming from the experimental data. The other one is from the model itself. So we can say that this one is the true value, quote unquote, and this one is the predicted value. Or you can call it another way. This one is the from the data. This one is from the model. Okay, predicted model value. When you take the difference between the two and you square the value, we call it squared error. And if you sum up everything here, then the result will be sum of squared error, SSE. All right, so SSE is just the sum of everything here. Okay, so please, what do you call it, enter all the formula as what I did just now, and then let me know once you're done, okay? It should be like this. And then if you to just double check your values, then maybe I can just increase the decimal places, okay, up to 3. So you can see what are the values for minus the CADT as well as the mechanism model, okay. Right, so please let me know once you're done so that we can move on to the next step. Okay, good. Aisha is done. So can I just get a few more answers from the rest of the students? Okay, one more, just one more, just to ensure that everybody is on the same pace. But if you're not done it, please let me know so that I can give you maybe 1 more minute. Done, eh? Okay, right. Right, so we have got SSE value, and SSE, we want to set it to be 0 or a number small enough that it is considered numerically 0. Okay, if you check on the menu here, there is a menu called data. Click on the data, and then you move to the all the way to the right. There is a solver icon there. So click on the solver icon. Okay, first of all, you click on the data from the menu. And then from this tab here, you can click on the solver. Okay, click on the solver icon. A pop-up window appears. The first thing that you can see here is that there is a cell here called set objective. What does it mean? It means that you want to set something to maximize or minimize or a value of something that you like. Okay, what is our objective? Remember that we want to set our SSE to 0, correct? So let's do so. Click on this arrow icon and then set the SSE. Just select the cell or type in the value. Is G23 in my case here. It could be a different cell in your case. So just click on it and then hit enter. And then set the value to be 0. Okay. And how are you going to do that? Well, I want to change some variables here. I click on the arrow again, and then I select these two cells here. Once I select these two cells here, I'm basically selecting M and also K, yeah, for Excel to consider in such a way that once it runs the optimization algorithm, it will give you a 0 value for the SSE. Okay, so once you have selected these two cells and hit enter. Okay, and there are additional things here also. For example, here, you want to ensure that M and K value are positive, right? So you could add a constraint. What is the first constraint? I set my M value here to be greater than equals to 0. Okay, so add one, and then add another one, which is my K value. I also want it to be greater than equals to 0, and then click OK. So basically, you have got the first one is that you have got your objective function, which is your SSE, and you want to set it to the value of 0. How are we going to do that? I'm going to change the value of M and also K, which is this cell here. And normally, I would just put them side by side because I can just select both cells together. I also can put in constraints. Here I've got two constraints. One is that my M value must be positive, which is my F28 cell here must be greater than or equals to 0. And similarly for my K, it must be greater than or equals to 0. And assuming that I want to touch any other options here, I can just click the solve button. So once I click the solve button, Excel will give me a solution. So you can see that just now the SSE was a different value. Now it is a number which is numerically 0, basically, because this is 0.0005. And then you can see that I click OK. You can see that my M value is 0.13 and my K value is now 18.8. So if you compare these values versus the one that you found from the linearization of the nonlinear kind of equation before, you can see the difference. Okay. So basically, well, I don't want to say that this one is more correct than the other, Yeah, but we could try another way of solving this problem. Yeah, so here there is an issue with regards to the let's say the CA value. Once I do this, yeah, minus dCA dt, I am taking basically these two values here, take the difference, and then divide that by the two values here for the t. But where is the exact location I should put in the value? Is it here or is it somewhere else? So that one is not something that we can be 100% certain. Another way of doing so is that, okay, I'm just going to do the same thing. Yeah, the CA on the numerator of the left hand side of the equation, which is minus delta CA over delta T. Just going to repeat the same procedure as what you see here. Okay, same thing. Okay, I create another column. I call it CA. Okay, can you create a column called CA? And the first value here is nothing but the average of the two value here. Okay, so you can use an average function and just select these two cells within the parentheses. So once you have done that, press enter and copy down the formula all the way to the last value. So the last value will take up the two values here, take the average within between these two values. Okay. So let me give you probably 1 minute to do so. This is quite straightforward. Remember, once you have entered the formula, you copy down the formula just like that. Okay. And we do not change this value here. Yeah. So you can just select the whole thing, copy, and then paste it somewhere to the right of the green block here. Right. So you can see that this is the MM model. Okay. I want us to start from, let's say, 1 for my M value and 1 for my K value. And you can see my MM model here give me a different values as compared to the one before. Okay, the one before was here after solving for M and K values. Okay, so here would be the initial predicted values, and I can do the same thing, finding the difference and then square the difference between the two, and this is what is termed as square error. And after that, do the same thing, copy down the formula. Copy down the formula all the way to the last row, and then sum up the whole square error, and we still call this as sum of square error, SSE. Okay. And how do this kind of approach different from here? Okay, now we have got the CA and we have got minus the CA dt. For my predicted value, yeah, rather than using the CA from the first table here, I use the CA, which is the transform CA value. Yeah, what is this? This value is the average between the two subsequent values. Okay, so whenever you see CA in the equation, you use this new value of the CA. Right. Can you do that? And then just copy down the formula like that. Okay, let me know whether you have done it. Okay, thanks Dimas for the hint. Go to the add-in and then find the solver add-in and then click on the option that you want the solver to be there. Okay. Right. So can I check with you whether you have done so? Meaning that done it. Okay, good. So once you have done that, we are going to repeat the same step as what we did before, but now we use the values in this blue block here. All right. So our objective is still SSA. So we click on data and find the solver icon here. Click on the solver icon. Okay. what I want to do is that set my objective function here, SSE, equals to 0. And don't worry, because Excel will try to minimize the value or find a value which is close to what you set here. Now my variables will be changed into these variables. Okay, not here. So it's going to be here. Yeah. Click enter. And I want to set the same constraints. I can choose not to set the constraints. You can try to do so and then see if your answers are different. And then you hit the solve button and let Excel do the job. Now you can see that the values for M and K are closer to the one that you can see from the linearized what do you call it, solution. So this one up to, let's say, one significant figure. M here is 0.2, here is also 0.2. Here is 20, here is also 20, yeah, up to one significant figure. So you can see that we have improved our what do you call it, way of finding solution a bit using the solver. Okay, and this is obtained by correct CA value, or the more accurate CA value is not this value here. So we have to take somewhere in between. And the easiest one is just to take the average. As you can see here, let me plot the concentration profile again. Okay, so you can see that there is a line here, which is a linear line between 0.1 and 0.2. And we are just taking the average between the two, yeah, and put it back at time 1. So basically, you take the average between these two, and then you bring the average to time equals to 1 hour. Yeah, because we are trying to find the corresponding predicted values with the minus dCAdt. So there is some uncertainty. Yeah, where is the value for the dCAdt should be at? Yeah. So this is another approach. Yeah, you can see that the model. The approach here gives you a more accurate answer, or something that is close enough, yeah, to the one that you found from the first approach. Okay, now we want to go a bit further. Yeah. Well, before this, we said that we are still going to use the sign at the same time, which is from 1 to 11, but we just move the CA values. We just take the average between the two subsequent values. What if I want to move my time also? Yeah. So this one is kept constant. Okay. And you just add another column here. We call it T column, the time. And the time column is nothing but the average between these two time here. Okay. So can you do so? I'll give you about 1 minute to do so. And once you're done, let me know. So Zihao, have you done that? Why is it too late? You cannot find the Excel solver, is it? Okay, can you locate the solver add-in? Okay, you could try later on, but I suggest that you try to find it as soon as you can right now, because you want to participate in this tutorial. Okay, good. You just add in the solver. Can you try to do what we did just now quickly? And then let me go back to Excel. Here, this is the first thing that you should do. And then after that, the first approach, and then the second approach here. And then we are now here. We are just trying to find the average of the t values. Okay, so I'm sure that you have done so. We are still going to go with the same approach. Let's start with m equals to 1 and then k equals to 1. Yeah, I don't know what those values are supposed to be initially, right? So I'm just going to put 1. And then my SSE here, okay, let me put in the SSE again. This is the SSE. Okay. So my SSE has now been increased from 0.0004 to 0.1, which is quite a huge value for the SSE. So I click on data and then go to the solver icon here. Click on the solver icon, and then now I want to set a new objective, which is this cell here. Do not select this cell, which is our previous approach. Select the appropriate SSE value, yeah, and hit enter. And again, set the value to 0 by changing select these m and k values rather than these m and k values. Okay, right, and then keeping the same constraint, click solve. Right, and click OK. So the result is not improving the accuracy of the solution basically. Yeah? So I can see that my m value here is 0.188. If I round it off, it's going to be 0.2. But then my k value is a bit far from the initial value here. The initial one was 20, but then the one that is obtained here is 16.6, which is a bit too far off. So as a conclusion, what I can say is that if you want to use the Excel solver or any built-in function in Excel, you just need to make sense of it. Number one is that it's not a magic. It is based on what you put in. Okay, so garbage in and garbage out. So what you can do is that the first approach here, we just use that minus dCA dt as our minus delta CA over delta T. So what we did, we just take the corresponding values of CA1 minus CA0 and T1 minus T0, right? And then compare the value with the model value, which is the equation on the right side of the equation. Yeah. So when you compare it, initially you started with 1 and 1 for m and k values respectively, and you got the squared error. And then after that, you sum up, you're going to get the sum of squared error at the bottom here. So once you compare these two values and you use Excel solver, you're going to get m and k values, and these are not as what you expected. And then you try to find a more improved, solution. Yeah. So what you could do is that rather than using the CA as 0.84 from the original data, you take the average between the two subsequent values, basically between these two values, and so on. And then you place that in the second row. Okay, so the value that you obtain here was obtained from the average of these two values here. Okay, the value from the same row as well as the value from the previous row. Your model will be utilizing this value, the new average value of the CA, rather than the value of the CA that you obtain experimentally. Yeah, why is that? Because we have uncertainty with regards to the minus dCA dt. You remember that you have learned about the integral approach as well as the differential approach, right? Once you want to sort of solve for the order of reaction and also the k value, yeah, from topic 2. So we have got quite an uncertainty regarding the differential method. Yeah? The integral method can give you a more accurate answer. So similarly, the argument is that minus dCA dt here, we are not sure where we are supposed to put in this value. Is it at t equals to 1 hour, or is it at t equals to 0.5 hour, or whatnot? But then what we can do is that our model, we can say that rather than depending on the CA value on the same row or at the same time, we could average out the value here. Basically, we take a linear value, the emit value between these two subsequent values. Okay, and then we can improve the answers. Yeah, so these are close to this one. We go further, but our answers are not as accurate as this one. So we stop here. Okay. Right. Can I check with you whether right now you know how to use the Excel solver, and then can you check whether you could use goal seek function for it? I'm sure that once you compare between the two, yeah, just in case you forgot about it, if you want to go and use the goal seek, is here under the data menu here, you go to the what if analysis and then you click on the goal seek. You can see goal seek, yeah. You can set the cell, which is your objective function. For example, here, I want to set this cell equals to 0. By changing, I can only change one cell, either M or K. I cannot change both of them. If I select both of them, I can select, but then when I hit OK, it will give me an error because here, this cell must be a single cell. Okay, so let me go and change it. So if I go to, let's say, goal seek again and set this one to 0, my SSC to 0 by changing my K value. Okay, and hit enter. Oh, basically I need to probably change the M and K value again from the the soft value using the solver to the one that I initially estimated. So let's start with M equals to 1 and K equals to 1 also. Again, you can go to the what if analysis and go to the goal seek and set the objective function here to 0. And then by changing K value, okay, and hit OK. And then just wait. So you can see that, the current value is a very huge number here. What does it mean? It means that basically goal seek cannot find an appropriate value for SSC, which was set to 0. And the difference between Excel solver and goal seek is that if you look in the solver window here, we can set the objective value to a value of 0, yes, as what we did for the goal seek function just now. Or if you're not sure about it, we can just select minimize this value here. If you want to perform optimization with the maximization, you can also do so. Click on the max button here. So you can either maximize the objective function, you could minimize the objective function, you could also set the objective function to a value. And for example, you have got a value on the left-hand side of the equation and the value on the right-hand side of the equation, which is calculated. Then you want to set the value to be equal to the value on the right-hand side of the equation. Yeah. So by changing what cell? Yeah. So the cell here you can select, and then you can select, multiple cells in solver. It's not limited to 2. So you can select, let's say, 3 or 4 different cells if you've got, let's say, 3 or 4 parameters to be solved simultaneously. And the other advantage of using the solver is that you can add constraints here. So constraints, for example, here we want to ensure that the M and K values are positive. So you could also, set them to be positive, which is setting the cell to be greater than or equals to 0. Okay. You could also set M to be an integer. So for example, here I can add another constraint here, and I can select M to be an integer. Yeah. Click add. So basically, I have selected M already, then it doesn't like it. So I can select, let's say, this cell here to be an integer and click OK. It must include only variable cell. Okay, so basically the variable cells are here. I already selected the M, so I cannot change it. What I can do is that maybe I can delete the constraint and add a new one and selecting here to become an integer. Still, it doesn't give me a must only variable cell. Okay, so the integer here is a bit tricky, but the rest of the constraints, I think you you can just select whether they are greater than certain value or less than certain value or even equal to certain value. You've got the options also as a binary variable, which is 0 to 0 and 1. And then there is also a diff. I'm not sure about diff here, but the rest of them I think is just self-explanatory. Okay. Right. So we are done with the solving the same problem here. Yeah. This is coming from tutorial in topic 2, question number 5. So rather than going through a very lengthy steps in order for you to find a linear equation or a linearized equation, and then from there you can determine the k and m value from the intercept as well as the slope, you could easily use a solver function in Excel in order for you to solve for the m and k values. So let me go back, and then this is just one last example. Click on the solver and set this SSE value by manipulating these variables without any constraints. So let's see whether Excel can solve it. Yes, it can solve, but the numbers here are quite not what you expected. Yeah. So let me go back to 1 and 1. Before this, the value for k was very high number. So it depends on your starting point, basically. Yeah. As what I showed you just now, if you pick, let's say 1 million, 1E6, then the solver may not be able to give you the right solution. Eh? Let's try that again. So if I pick on the same thing, my SSE here to a value of 0, let's say I want to just minimize it rather than setting it to 0 by changing this variable. So changing these variables here without any constraints, and let's see whether Excel can give me a solution. So the solution here is not as good. Yeah. So lesson learned. The starting values or the initial values that you set for m and k or any parameters that you want to solve must be as close to the final solution as possible. So this comes from the prior knowledge or from the literature review. Okay? So let's go back to 1 and 1. And then from here, I set my SSE to be minimized by changing these two cells values and click the solve button. If you recall that these were the same values that we got from setting the objective function to 0. So I could have two options now. One is setting my objective function to 0, which means that I want to set my SSE to 0. Or I could ask Excel, can you just minimize this value here, this SSE to a very, very low number, yeah, so that I can get my m and k values. Okay, right. So let me see whether there is a question. Can see your orange column CA for t equals to 1.5. Yes, you can. Yeah. Oh, basically over here I took the values from this one. Yeah, I was experimenting just now. Sorry about that. Maybe you took the value from here. Okay, so we could do so. Thank you very much for the answer. The what do you call it? The reminder just now. So the average for this one here, I could take the average of this, and then again copy down the values. Right. So I've got different values here. So does that answer your question, Jason? Or maybe you want to see what do you call it, the solution for this one, whether we can have an improvement or not. So before this, I used these two values and so on, these two values, yeah, in order for me to find the new CA values. Yeah, and then because of that, I did not get good values for the M and K. Okay, so we'll take just a minute to use the solver. Again, set the SSE to 0 by minimizing the function here, objective function, and then by changing the variables here. Setting no constraints, and then just click solve. Okay, so you can see that we are basically overestimating the values for M and K. So rather than 0.2, we have got 0.3, rather than 20, we have got 22.2. Okay, right. So this approach is much better. Yeah. So just remember, yeah, where is to put your CA values, or what is the appropriate CA values that you need to put in every row. Right. I think we have gone through the tutorial quite lengthy, yeah, kind of way. But I'm happy to do that because I think this is a good knowledge for you to have or to possess before you graduate from Harvard Watt. Yeah. We don't want to hear any comments from industry later on saying that Harvard Watt students do not know how to use Solver. That would be quite embarrassing. Yeah. Because Solver is just one of the most basic tools to be used in Excel. Okay. All right. So before we move on to the tutorial on topic 3, do you have any questions with regard to the Solver? No? Okay, good. All right. So I'm going to stop the recording here because I would like to share